Hello, everyone. Thanks for being here, and thanks for having endured the entire day and being here at this last session. I hope I can make it to make you enthusiastic about WebAssembly, and I want to introduce you Chicory. Just a word about myself. I'm Andrea Peruffo. Those are my contacts on X and GitHub, and I work for Red Hat as a principal software engineer. Reach me out wherever you have questions, especially about WebAssembly, etc. So, I don't want to give nothing for granted, and I want to start from the very basic of WebAssembly. Even if you have heard this earlier in another presentation or at other places, I would just want to reiterate over what is WebAssembly and why it is important. Let's go quick about on it. WebAssembly, first of all, is a binary format. Machines are really good at understanding bits and numbers, and a binary format is ideal for sharing code across machines over a network. And machines are really good at interpreting and understanding it. We are not that good, so there is a conversion that you can converters that you can use to convert the binary format to a text format that shows you a much more readable version of your program and your Wasm module. As you can see, there is a kind of a Lisp syntax with a lot of parentheses. It is not Lisp at all because this is not functional at all, but you can read it, you can understand what is going on, and you can have an idea of what this means. But the Wasm format describes the fact that those are runnable, executable programs. So from the function that we defined here, which is an add function in this case, you know that once you have described and compiled it in a format which is Wasm, you can execute somehow this function, passing 2 arguments and getting the expected result. So this is in essence what it is. And how, the specification describes how the machine should do it, and this is a stack machine. If you are, if you know the JVM, or this is that is a stack machine as well, or you are into compilers or interpreters, this should sound very familiar to you. So you just get a local variable that the user provided, push it on a stack, which is a data structure last in, first out. And you take the first argument, you push it on the stack. You take the second argument, you push it on the stack. You perform the addition that we have seen in the code here. So you go from the inner blocks to the most outer blocks. And you perform the addition by popping one value from the stack, popping the other value, and pushing, again, the result of this function. Easy, right? If you're familiar, as I said, with the JVM, this is bytecode. And it looks exactly the very same thing as we have seen in Wasm. So there are a lot of similarities in between WebAssembly and what the JVM is doing in reality. There is a peculiar thing that the Wasm specification describes, that is saying about facilitating interactions. So Wasm, WebAssembly, is defined and is built to be embedded in other languages and runtimes. It has been designed for this. So you have an host languages. In this case, there is Go, but we want to see what this means for you, so we will use Java. And there are 2 parts of it. So the host language can call functions described into the Wasm module. And this is, for example, executing the add function that we have seen. This is executing an exported function from the Wasm module. Or the Wasm module can call functions imported from the host. And this is very important because this gives powers and makes your WAS programs extensible by themselves. So, which problems WebAssembly solves? Why it has been invented? So, the first one is sandbox execution. We have talked briefly about call imported functions because WebAssembly modules per se doesn't have any capability, so is not able to access even standard in or standard out on your machine. Is not able to read a file. Is not able to read the input of your keyboard or to draw anything on your screen. So the Wasm executed without giving it context is just a very, very nice and sophisticated calculator. And this is very safe. This means that the host runtime have to provide granularly all the capabilities that the Wasm function can use. This makes it extremely secure and extremely sandboxed. Memory control. So we have, since we have sandbox execution, we also want to control very, very granularly how much memory is being used by your Wasm module. And in this case, the memory has is being defined as a data structure in the host. And the host has complete control over the fact that this memory can be grown, can be shrinked, or can be defined to a specific size. So you know exactly within your Java process how much memory will be given to the host function. So you have, again, a lot of control over it. Speed. Wasm has been built to overcome the limitations of having to compile JavaScript in the client side. So the Wasm format resembles assembly code at the end of the day, and it is designed to be highly optimizable for different hardware. So one of the goals of the specification itself is to make the code that gets executed through a WAS module very, very, very fast. And that's how it is designed. And this is a standard, W3C. So this means that you will be relying on people being able to working together toward implementing and working with something that is a standard. You don't need any more embedded languages like Lua, etc., that will be just implemented by someone, maybe someone great, but it will be just one person or a team implementing the both sides, how to embed it, how to execute it. In this case, it is a standard, and you can rely on it. It's not going away anytime soon. And where is it used? Even if you don't know about it, this is used in the web browser, and in every web browser, and in a lot of applications. Google is using it for Google Maps, Excel, Word. So if you're using those kind of applications through your web browser, you are already using Wasm behind the scenes without even noticing. And this is not going anywhere. So this is going to remain. Function as a service. As I told you, the Wasm specification defines very, very well the limits of the functions that will be executed. So running in process a Wasm module is very secure, doesn't compromise the security of your application, and enable you to give more functionality to the user, or to implement serverless functions, or to implement those kind of things. And the part that we will concentrate on today, which is building extensions. So you can extend your software through Wasm modules because they are secure, they are small, and they can be written in very different programming languages. So it's easy to make your application extensible and usable and tunable programmatically by your users. When we speak about WebAssembly, there are always two separate things that we have to think about, and there is a lot of confusion about it every time you speak with someone. The first one is that you have programming languages and you can compile those programming languages to WebAssembly. Let's look at an example. In this example, I have an operation. I'm describing very similarly to how I did with pure Wasm code, but this time I'm writing Go, just because it's convenient and is very well integrated. And you can actually implement a function, in this case is an operation, that will take 2 integers and return an integer again. This is very basic. I know it's an hello world, but it gives you an idea of what it means using and extending applications using WebAssembly. In this case, I'm using TinyGo, and you can really easily compile this simple function that is just an operation in this case, using TinyGo and having a Wasm file as an output. The second part is executing Wasm code. So again, the story of host and guest language. Now we have seen how to compile a guest language to Wasm. Now we want to see how to execute this Wasm code in our application. And this is where we introduce Chicory, because Chicory is a runtime for Wasm written in pure Java. So let's look at some code that might be familiar to you. And I have here just a super simple demo application of a Spring Boot server. And for the sake of the presentation, I already implemented the bulk of the code for having mapped the 2 endpoints, because very likely, if you're here and you are a Java developer, you are probably doing web applications, or very likely, and you have seen about them a lot. And here we have 2 endpoints implemented. One is upload, which makes you able to upload the binary format, so the Wasm file of a Wasm module, so that it will be loaded into the server for future utilization. And the second endpoint is compute, that will take 2 integers, do something, passing them to the underlying module, and return the result as you expect. Integrating it with, so at the moment the implementation is empty, so there is nothing that runs here. We can run our applications, and I have here the curl commands to trigger the 2 endpoints, but it will do nothing. Oh, yeah, Wasm uploaded, because, of course, this is not doing nothing and not throwing an error in this case. But let's implement it. So once we have the bytes that compose our module, the first thing that we should do is to parse them with a parser. So understand what is written inside those bytes. And we have to store this module, this Wasm module, into just a private field in this case. Let's keep it simple. Let's not care about how we will implement multi-tenancy or whatever on top of it, but let's just make it simple for this demo and see that here, after you upload some Wasm bytes, you get a Wasm module loaded. How do you compute and trigger the implementation of this Wasm module? Now you have to create an instance, which is an executable, a runnable instance of the Wasm module. So here instance.builder. We have some builder thing here going on, and this will be an instance. So on this instance, we have to call an exported function, like I've explained to you before, and it will be called, the exported function has been called operation, if I recall correctly. Yes, so operation, let's just call it, and apply it with the two operands that we have. WebAssembly has a peculiarity, so the returned results can be more than one. So it's an array of results, and we just want to take the first element of it. So here we have the result, and then we want to return the result, which in this case is a long, but we just typecast it to an int, and that would be it. Now let me restart our my simple Spring application, and now I can trigger again the endpoints. Now I upload the Go code that I have implemented to implement actually this operation, and now I can trigger the compute function. Here, with a couple of numbers, we have seen that I'm passing OP1 and OP2, the two operands are 5 and 3, and this is returning the sum, which is 8. Now, what it means for your user. Your user are able to, for example, to multiply this for 10 or to do anything anything with it. And you can just rebuild and upload again the Wasm module and pass, for example, a different number here, and you have the expected result. So this makes it extremely easy in just a few lines of code to make your application customizable by your user. And this is a great power. Now, we have a little time, so I want to show you something. There are interpreters, and there are host machines that are shipped as CLIs. So you know CLIs, just command line executables. And in this case, you can use Wasm interp, which is a tool for running a Wasm module, running an exported function by passing the arguments. So if I run this from the command line, I have the expected result. So this is the function, the operation that I just compiled. But what happened? That this tool, in this case, this is a CLI written in C and C++ that can be compiled to Wasm by itself. So what it means is that I can actually embed it in my application. This requires a little more code, so for the interest of time, I'm not going to implement it straight away. That what is happening here is just that I'm instantiating a new sandbox file system, and I'm running. You can see exactly what you have seen before. So I'm invoking the CLI inside my server-side application to get the result. The result of a CLI is a string, so I have actually to take the result and calculate where the number is to return you the correct number. But this is a detail. But this is just another of the great things that Wasm can do for you. You can take CLI applications, which are written in various programming languages, Rust, C, Go, and just run them in your Java application. And now here I have to upload the Wasm and get my operation again. And this is working again. I can change my operation and upload something different. I don't know, whatever. Please.
How can I make sure that
So you have control of it. Here, in this case, I'm not exposing the file system of the machine. What I'm exposing is just a virtual file system. I'm using, I don't know if you're familiar with it, GMFS, which is a virtual file system. So it is implementing the file system API, but it is actually completely in memory. So this is completely safe, and it is not touching the files on your machine. And this is one part of your question. The second part is running in endless loop. And the fact that you have control over the thread that is actually running this application means that you can set a timeout for this request, for example, and interrupt the thread. Chicory will respect the thread to be interrupted and will kill the application. There are more sophisticated ways for doing it. I encourage you to come and speak after this talk or tomorrow, because there are various techniques for preventing infinite loops or an enormous amount of resources used by the user function. So you have ways of controlling this thing. Now, we have seen how to execute a CLI, but you can do a ton of other super interesting stuffs with WebAssembly. For example, just to give you another example, it exists a framework called OPA, Open Policy Agent, which defines a language that helps you write rules for authorization, but that are normally used for authorization. So you can enable the access to some resources or disable the access to some resources based on those rules. And in this case, I want to write a super simple rule. And the cool fact is the fact that those rules can be compiled to Wasm and executed as Wasm modules as well. And there are a ton of those examples. In this case, I'm just saying I want to implement a very simple rule that will deny the access to everyone that is not Alice in the username. So you can implement your Rego. This is the language. This is a data log similar language that enable you to write those rules. So here, if I change the name to Bob, you can evaluate, and you have an allow that is false, and back to the known Alice, you have, again, the result here. What it means for you? This means that you can actually have the very same application that I showed you before, but now I can have an interceptor that can do the authorization for you in your Spring application. So imagine that you want to add authorization to customizable authorization to your program. This is one way you can do it, and this is interoperable with many other languages and many other tool chains. For example, in this case, the OPA compiler can compile your Rego rules and execute and we can, through Chicory, run them in Java. I have been building some SDK on top of those rules because they make it easier to be used in a Java application, but it's just kind of an abstraction level over the very low-level primitives that I've shown you before. In this case, I have OPA. I can load the policy. In this case, it's a static policy compiled to Wasm. I have it here. So this is my policy, and the command for compiling it is OPA build, etc., and it will output the policy.wasm that we expect. So we can actually go there, and I can build it. Oh, yeah, that's fine. So now I have my policy.wasm. I can run my server, and in my server, what happened is that in the interceptor that I have implemented here, I can actually have a prehandle that check if the request is a get, and if it has an header, which is a X user, then I want to run evaluate on the policy that I just defined, and passing to it just the JSONified input as you have seen in this playground. So I'm passing something very, very, very similar to this. Here we can again run our Spring Boot application, but should do the very same as before. So I have to upload again a Wasm file, but at this point I have a slightly different command to run, curl command to run, that defines the header. So running the header here means that, for example, I'm saying that this user is Bob, and I want to get something. In this case, it returned that the user is not authorized to access this resource, and it is actually returning the expected 401 result. If we change the user to be Alice, in this case, the operation is actually performed. And this is the new operation that someone has uploaded. Since we have had another wonderful talk about Wasm, I want to show you even another way you can run WebAssembly, or why you should be interested in WebAssembly. That is for gaming, of course. So I can actually run Doom in a fantastic Swing application, because Doom can be compiled to Wasm, and I can actually, yes, play the game and go and kill people, go and kill monsters here around here. I'm probably not that good at Doom. Playing it on stage is not going to make it any better. But yeah, you can again. This is a C application. Is really easy to port to other targets. In this case, it has been compiled to Wasm, and is again runnable through using Chicory on plain plain JVM. And there are a number of different use cases. You can run just native code for your Kafka application for doing transformations. Red Panda is using a node behind the scenes to enable you to run transformations using Wasm, and a ton of different other use cases that you can actually implement and run using runtime in Java. And yeah, I would say that this is it. So those are the links to the repository of Chicory and to this presentation. Please go there, check the resources out, and I hope that you will have fun and reach out if you have any question. We have also a Zulip channel for chatting with the maintainer of Chicory. So reach out, and I'm happy to talk to all of you. Thank you. We have time for one question, I guess. Please. Yes. So thank you, because every talk should have this question. And we are talking about implementation trade-offs. So the goal is the same. We are running Wasm code inside the JVM, in pure JVM, but the trade-offs are completely different. So with Truffle, you are they built a Wasm interpreter that is running in GraalVM and can be optimized with just-in-time compilation and the GraalVM technology. What we have done is to start on a plain and standard JVM and write a pure interpreter that doesn't have any dependency. And on the other side, we are working toward having an AOT compiler that basically takes your Wasm your Wasm binary format and translates it one-to-one to Java bytecode. We can already run quite a bunch of application on it. It's not finalized. It needs a little bit of more work, so we call it experimental for the moment, but it will be available in a matter of time. So same goals, different trade-offs. Yes? No, in the sense that the WebAssembly specification describes quite a bunch of extensions. One of them is threading, but is not implemented by a lot of runtimes, and we are not implementing it at the moment. So for the part of calling and executing asynchronously, this doesn't work. But what you can do is having callback, because your host functions will be called from the guest module. So if you have a Wasm module that you want to call outside a custom Java function, this is extremely easy to be done. Anyone else? You can find me outside. Thank you.
All systems are nominal. Initialize Genesis sequence.